Okay, I think it's recording, so it should be fine. Let's see. Try again. Okay, need to admit Maxwell. Okay, we have Maxwell too. Okay, great. So everyone, if you can just mute yourself, that would be great. So we don't hear the background noise. Let's just have a recap of what we covered in last lecture. We talked about these different methods, or let's say different types that steps that we need to really move from the step one, which was about the understanding of the physics, to the next steps to really generate or make our numerical simulation for these finite different method schemes. We talked about different differential equations, different types, um, different physics. We talked about different types of ODEs and PDEs, different types. What is homogeneous versus heterogeneous, for example, or what are different well-known ODEs and PDEs in nature. We talked about this simple spring analogy, and these five basic equations of Laplace, diffusion, advection, diffusion, and wave equations. And these are really the five that we will work on in this semester, really. And you need to build upon these five different equations to build your final, project. As we talked about this initial condition, the boundary condition, and I think this was the last slide that I stopped here. And it's really about the foundation of a finite different method simulation, which is about a discretization. So how we need to discretize a system to approximate our unknown function along these different finite number of points. So let's start to talk about this discretization. Then we're going to talk about the Taylor series and how we can build your finite difference scheme to solve for a few simple problems. Probably at the end of the lecture, if we have time, we're going to work on a very simple advection problem in Excel. From the next lecture, you need to be ready to have at least MATLAB downloaded or installed on your PC and computer. If you have not done that so far, I will give you some direction on Brightspace. And if you have any problem in downloading and installing installation of the MATLAB, just let me know. But that should be ready just by the next Monday. Today, at most, if we have time, we're going to work just on a very simple example on Excel. So let's talk about this discretization. So we found that this should be happen in two different systems of time and space, because most of our equation, basically they are time dependent and they are space dependent, depending on if it's 2D or 3D. In space, let's say I have a predefined example, and in most of the lecture I use this, example of a pollution in a 2D domain. And let's say if this is a pure advection, I have some initial condition. Let's say at T equal to T naught, I know that, okay, this is the concentration of my chemicals in the domain. And the question is how this gonna move in a pure advection at any given time. So let's say if I know that I like to find or predict my system at T equal to Tn, and let's say if this is a solution, then how I can actually predict this in time. So we need to discretize this domain in time as well, right? And discretize means, well, splitting the time between my time 0 to Tn to several finite number of times. So in time, my next step would be T, which is say ti, t naught plus my delta t. Then the next step is just t naught plus 2 delta t, and so on, until I reach the final stage, right? So it's about the discretization in time. On the other hand, we have the discretization in space. So if this is my domain, I need to approximate my unknown function in finite number of points. And we talk about this why finite, because, well, we have a limited cost, limited time and cost and ability. So we need to really simplify the system. And once we build these grids, we can approximate our unknown function only on this finite number of nodes or grids, right? So let's say if this is my solution in reality, right? I can just approximate my value at this point, which is right on my grid. And I'm not able to find anything for this point because it's not on my grid, right? So of course, we have a finer mesh or grid points. You would have more ability to really approximate the system along a more accurate grid data or grid points, right? And most probably, we're going to talk about this, but most probably discretization, having a higher mesh or finer mesh, let's say, in time and space will give you more accurate result, but that's not the case for some cases. So we're going to talk about these convergence problems later. But for discretization, now let's define this general form of our unknown function. So this is, we talked about discretization in time and space. And let's say this is my y, this is my x, right? So now my unknown function can be written in a discretized form. How? Well, we have a superscript. Let's call this n. And it's talking about the time grid or the nodes in time. And on the other hand, you have these subscripts of I, j, and k. And these are the IDs of my grid points in x, y, and z. So at most, we have a three-dimensional space. So let me give you an example. Okay, let's say this is my grid. So I have a very large mesh size, or a grid size of, let's say, 4 grids for x and y. So the grid for my x is starting from I equal to 1, and I is really the ID of my x grid, right? To I equal to 2, 3, 4, and 5. And then here, j, again, starting from this point of 2, 3, 4, and 5. So let's say if I like to find my unknown function at time interval of 5, but in this case, we don't see the time grid, we just see the space grid. And let's say for I equal to 5 and j equal to 3. What does that mean? Well, we're talking about this is 5 for x, right? And for y, this is 3. So we are really talking about this point. And by this representation, you can basically point out your pointer, or let's say you can march on your grid using this representation, right? In time and in space. Okay, now let's see how we can actually approximate or find our unknown function using this discretized form. And that's gonna be everything about this Taylor series. So in finite difference method, we're gonna use this Taylor approximation. You may have seen this before, or we have heard about these, Fourier series and all these different series. This is really the most simplest way of approximation, and it has actually worked for many of the physics that we are going to cover. So this is an approximation scheme, and the fundamental is very basic. Let's see how does this work. Okay, this is our unknown function. Let's say an unknown function, this is just an example, right? This is just a function of x. So it's not even time dependent. It's the simplest case that you can imagine. And then the question is, if you have, or if you know your unknown function for a given initial value, right? Let's say if this is known only for x naught, it's kind of initial value, right? Then the question is, can you guess or can you approximate your unknown function in the vicinity of your known value? So let's say this is x naught plus delta x. So very close to what you have in your known system. Can you guess what is the approximation for you close to the point that is known, right? So that's the question that Taylor has actually the answer for that. So in Taylor series, or let me actually draw this figure too. Let's say if I draw my unknown function in the y-axis versus the x-axis, and there is no time, right? Because this is a form of the equation that I just defined. It's not even the differential equation. It has a theoretical value. And let's say the theoretical value is, or the equation is in the form of a concave, or let's say parabolic system. So this is the analytical solution, right? Okay, let's see what does this mean. Well, we have at x naught, right? This is known. So you only have the information of this point. This is u at x. So the question is, can you find this unknown function at this point, which is x naught plus delta x, right? And this is really your space interval. So without having the analytical solution, can you guess what is u at x naught plus delta x? Okay, let's see how Taylor solved this problem. So in a Taylor series, any unknown function can have n continuous, or can be written in a form of n continuous derivations. How does this work? Well, in a Taylor series, u x naught plus delta x, this is what we are looking for, right, is equal to your initial condition, or the unknown function at the initial condition, plus the interval times the first derivation of your unknown function at x naught, plus your grid size, or again, the intervals, now with the power of 2 times the second derivative of your unknown function, again at x naught, but now divided by 2 factorial, right? And you know the factorial, right? N factorial means 1 times 2 times 3 times n, right? So this is the factorial form, plus, well, n continuous functions, right? So you can write really the general form as delta x to the power of n minus 1 divided by n minus 1 factorial times u unknown function derivative to the n minus 1 at x naught. So this is really the final form of a Taylor series. So let's see how we can use this Taylor series to find approximation for a case. And this looks very freaky, right? You have a lot of these functions and derivatives, but the good news is that you don't need to use all of them, right? In any finite difference method, on any simulation or numerical method or scheme that use a Taylor series, you need to just truncate the system in the first order or the second order. In some special cases, some physics which we are not going to cover, you may need to truncate this system to the third order. All the other terms, you don't really need them unless there is a special case. And if you add actually more data or more terms into your Taylor series, you're gonna need more time to simulate your system. So now let's see if how we can use this Taylor series only by truncating the system in the first order of the derivatives. So we are truncating this into the first order. Okay, let's draw again this graph. I have u versus x. And this is my analytical solution. Okay, if I truncate this in the first order, this is my form of equation. U at x naught plus delta x is going to be only u at x naught plus delta x times ux at x naught. This is my initial condition at x naught. So let's see what is this equation is telling me, right? I need to multiply delta x with the derivative of u at x naught. And what is the meaning of this derivative in terms of the graph?
It's the slope.
It's a slope, right?
Not
Exactly.
right.
So it's the slope of this line tangent to the theoretical value, right? So if I draw the slope, let's just draw the slope tangent to slope, right? To this line. Let's say this is the slope, which is exactly equal to this term, right? Okay, what is the slope? Well, my slope is y divided by x, right? So my y term here, let's see, what does that mean? I'm moving from x naught to x naught plus delta x, right? This is what I'm trying to find. So this is x naught plus delta x, and this distance is delta x. Okay, let's move up. So this value right here, this is also equal to u at x naught, right? So if I draw this slope, and add this distance to what I had initially, then I can guess basically my u at x naught plus delta x. And it's an approximation, right? So it's not exactly equal to the theoretical value, but it's an approximation. So I need the slope of this line, right? And the slope is height divided by the width, right? So the height is, let's say, y, which is height divided by delta x, right? This is equal to u at x, the first derivative of u at x, right? This is the slope. So in this case, my y, or the height of this line, this is equal to, I'm just writing everything for the y. It's going to be delta x times ux, x naught. So this is exactly what we have on this term, right? And it's just telling to us that if you know the first derivative of your unknown function at this point, if you multiply this by delta x, you can guess this height. And if you add this height to what you had initially, right, then you can guess what is your final unknown function at this given unknown point. But this should be close enough to what you had initially, right? So in this case, using the first truncation of the finite difference method or a Taylor series, you can really approximate your unknown function. Any question? Is it clear? Okay, so let's see how we can use this. I see a message. Okay, Khalid, do you have any question? Because I see your hands up, or?
Oh yeah, I just wanted to make sure that the first term should have been multiplied by 1 factorial. Divided by 1 factorial, right?
Yeah, so exactly. So this is 1 factorial, which is equal to 1, right?
Mhm.
So we don't actually write it here, but that is true. So this should be also 1 factorial, 2 factorial, 3, 4, 5, right? And in here, really, it's about the order of your derivatives, right? This is the first order. So the n here uh, is 1, 2, 3, and so on. Sorry, and is a term for a term, right? So this is 1, this is 2, 3, 4.
Yeah.
Okay, let's move on. Let's start this finite difference method. Or FDM. Okay, so we're going to use this method to start our numerical simulation or computational work. Can you tell me what does this finite mean? Okay, as I explained, we have finite number of grids, right? And this is in time, in space. So you should be able to find your derivative or approximate your derivative an unknown function in time and space, right? And the other meaning of this finite is that you actually have finite number of Taylor uh, series terms, right? So you cannot use all these terms because it's going to be really costly. You have to truncate the system to 1, 2, or the third order of the magnitude of for the derivatives. So for now, let's just focus on the first order FDM. It means that we need to truncate our Taylor series only on the first order of the derivatives. And if this is true, we know that right? For the simplest case, which our function was only a function of, or unknown function was only a function of x, so x naught plus delta x is going to be u at x naught plus delta x times the derivative to the x. So what Taylor is trying to give us is to find this unknown function, but then you can actually find this first derivative first. So if I write everything in terms of this first derivative, that is going to help me a lot because all these PDs, right, or ODs, they are in the form of the derivations. So let's just write this first order FDM or the Taylor series in terms of my derivative. So if I rewrite everything, the first derivative of my unknown function can be approximated by unknown function at x naught plus delta x minus the unknown function at x naught divided by delta x. And you see this really simple form of an approximation. And I think you can think about the meaning of this equation, right? It's very simple. So what is this trying to say? And this is really your step or a step size. depending on your derivative, either is in the with respect to space, well, this is the x size or y size, or in time, this should be the time size, right? So let's say if this is a one-dimensional system, and these are your points or grids to approximate your unknown function. Let's say if this point right here, this is your initial condition. So this is known, right? So you can use the next point, which is u at x naught plus delta x, to find the derivative at x naught, right? So because you're using the next point to find the first derivative, we call this actually a forward FDM. So we have different schemes. We're going to talk about this backward FDM or even the central FDM. But the one that I'm showing you here, this is just using the next point to find the first derivative at this point, right? So this is how we can find the first derivative of the unknown function using the forward FDMs. Okay, let's do a very simple example together. Okay, I think by now you might be confused, but once you solve for this example, you should have a better idea. This is example 1. Let's say I have an unknown function and the analytical solution is given, right? So ux, when an unknown function is just a function of x, and this is equal to x2. And this is my question. By using the first order forward FDM, give me the approximation for the first derivative of x at point 3. You're gonna wait for a few minutes, and once you have the result, just let me know. And this is the form, right? By FDM or forward FDM, the form is sorry, this should be the delta x.
Professor,
Yes,
what should we take as the step size, delta x?
that's a good question. So I didn't give you the step size. For part A, let's just use delta x as 0.1.
The result is 6.1, doctor.
Yeah, 6
That
point.
is, yeah, that is correct. That's correct. Okay, so simple, right? The first derivative of x can be approximated by this equation, which is right here. So my unknown function is going to be x2, right? So if this is x2, then this term is going to be, let's see what is happening here. I'll just select. Okay, no, it's fine. It's going to be 3 plus the step size, which is 0.1 to the power of 2, minus second term, right? Unknown function at x naught, which is only 3 to the power 2 divided by a step size, which is 0.1. So this is going to be 6.1, right? And the error here is really, what is the error? How much error we have? Okay, we have a theoretical equation, right? So what is the first derivative of this function? It's 2x, right? You just take the derivative. So
6.
yeah, so the x that we are interested to find, our approximation is at 3, right? So if you put 3, then the first derivative, the derivative of u, is going to be 6 at the end. However, our approximation actually shows 6.1. So really our error is how much? 6.1 minus 6 divided by the initial value, right? So 0.1 divided by 6. That's our error, and we can multiply this by 100 to get the error percentage. Okay, what would happen if you decrease the step size to 0.05? Then again, this is my first derivative at x naught, which is now is 3. So this is going to be approximated by 3 plus 0.05 to the 2 minus 3.05, and at the end, the result is going to be 6.05, right? So the error has really decreased by 50%. So this is how you can actually decrease the step size sometimes to get you to the more accurate result. Any question? Okay, good. So let's see how the other schemes of the finite difference method would work. And if you need more time, just let me know to take the note for taking the note. Otherwise, I can move to the next slide. Okay, so I already talked about this FDM, the first order. And I use only the forward method. So in this case, my first derivative is going to be ux at x naught, and I'm using the next point, which is x naught plus delta x, right, to approximate my first derivative at x naught. So in terms of this simple graph, this is my given point, or x naught, and I'm trying to use the next point to approximate the first derivative. Okay, what would happen if I try to use not the next point, right, but something actually behind this point, which is the backward point. So we call this FDM backward. And let's try to write the equation. So this is going to be the same thing. However, here you have your unknown function at x naught, then minus the u at the previous point is divided by delta x. So it's kind of the same thing, but then you are trying to use the backward point, right? So this is the current point, and I'm using this point to approximate my unknown function minus delta x. So why we need to have two different methods like forward and backward? We're going to talk about this some physics. or some problems depending on the initial and boundary condition, they may not actually converge when you use one of these methods. So you need to be careful about this. And sometimes even a backward method would not work for you. So we have actually another type of first order finite different schemes. This is not really the first order. This is kind of a second order. It's central. So let's see how you can use a central scheme. Okay, I'm gonna use the second order truncation, right? So this is my Taylor series. Now I'm gonna truncate the system right here. Let's write the equation for u in forward. So x naught plus delta x. This can be approximate. I'm just writing the Taylor series, right? X naught plus delta x, the first derivative plus the second derivative, what I should have delta x2 divided by 2, or 2 factorial, which is 2, uxx at x naught. Now I'm going to write the Taylor series in backward, okay? So u at x naught minus delta x is going to be u at x naught minus delta x at ux at x naught plus delta x2 to the 2 uxx x naught. So let's say if this is your grid, right? And you're trying to find your unknown function at this point, you're trying to use both these forward and backward points. So the first term here is using the Taylor series for the forward and the second one for the backward, right? And now we can actually do a trick. Let me show you. So we're going to combine these two. Okay, so if I subtract the second equation from the first one, right? Let's just subtract the second equation from the first one. Let's see what would happen. These two will be cancelled, right? These two will be also cancelled. So at the end, if I write everything in terms of this term, which is the first derivative of ux, right? My ux at x naught can be approximated by the unknown function in the next grid minus the unknown function in the previous grid divided by, let me see if I can move this to, okay, 2 delta x. So this is my final form of central FDM scheme, which is interesting because you are trying to use the forward and backward points to find a solution for your central point, right? That's why you call this a central finite difference method. In terms of this graph, it's almost easy to grasp that idea, right? This is your x naught. You're trying to connect these 2 points, right? Make a slope, which is a secant slope. And by using this slope, you're trying to be as close as to your theoretical value, right? And this is your approximation. So this is really the idea of having a second order central FDM. Any questions so far? Okay, now let's try to write all these 3 equations of forward, backward, and central in a discretized form, right? And what is a discretized form? This is a discretized form, right? We already talked about this. So let's see how to write this. And once we write this in a discretized form, then we are ready to really start our simple simulation. Okay, discretized form of these FDM schemes. Okay, I'm gonna write everything for this very simple unknown function of u is equal to f as a function of x, right? No time, no y. And this is my discretized form. And the superscript, I need to write everything in a time grid. And in the subscript, I have I, j, k for the space grid. So in this special case, there is no time, there is no j, there is no k, right? Everything is in terms of the x. And these are for the space grid. So the forward FDM in the form of the discretized system, well, this is my derivation, right? My derivation of my unknown function with respect to x can be approximated by, and you give me the answer. What should I write here? So this is your grid, right? I'm talking about the x grid. So I'm standing on the grid of I need to use I plus 1 and I minus 1, right? But this is a forward scheme. So if you are on this point, you need to use the next point, right? So let's write this. My unknown function at point I plus 1 minus my unknown function at I divided by delta x, right? This is a discretized form to find the derivative of your unknown function. What was the general form? This is the general form, right? We're just trying to write everything in a discretized form. So let me copy this and paste on the next page. Maybe you want to get a better idea. And this is only for the forward, right? Okay, now tell me the solution for the backward. What is the derivation of u with respect to x in the backward scheme?
Doctor, it's gonna be ui minus u subscript
Mm-hmm.
I minus u subscript I minus 1, exactly,
Mm-hmm.
divided by delta x.
Exactly. So I'm on this point, right? Okay, in the forward method, this is my current point, and I'm using the next point. Here, this is my current point, which is I, and I'm using the backward point, right? So this is how you need to write your equation. And we have a central. So my derivation to x is going to be, this is my current point, right? And I'm going to use both I plus 1 and I minus 1 to approximate the derivative of my unknown function at I, right? So my approximation is going to be u at I plus 1 minus u I minus 1, right? And remember this graph, right? Because we are trying to connect the next point to the previous point, then your delta x here is going to be 2 delta x, right? So on the denominator, you have 2 delta x. This is the difference between the forward, backward with the central point, right? You always have 2 delta x. This is also the difference that you are using the next point and the previous point. Is this clear? Any question? Okay. Can you tell me what is, if this is my unknown function, if this is a function of t, or it's only the function of time, right? And let's say I would like to find the derivative of u with respect to t using the central scheme. Can you tell me what is the equation in the discretized form? And this is the discretized form, right?
It will be u to the power t plus 1 minus u to the power t minus 1
Exactly, and divided by
divided by 2 del t x. Sorry,
delta t.
2 del t.
Delta t, right? So u, well, we're going to use the next time step. So we're going to use this n, right? Let's say n plus 1, because it's the next time step is on the superscript because we are talking about the time, not the space, right? It's central. So next time divided by the previous time. And this is going to be divided by 2 delta t, right? So this is really how we can write this in the central scheme. For forward, this is going to be u n plus 1, right, minus u at n divided by delta t. For backward, it's going to be u n minus u n minus 1 divided by delta t, right? So always just ask this question from yourself. If you're using forward, you need to use the next value, right? If it's backward, the previous value, and central, forward and backward. And you need to also be careful about is if this is over the time or over the space. Okay, now let's make it, let's move forward just one step. Okay, because most of the partial differential equations that we use, they are not either with respect to only x or t, but it's also a function of another variable, right? So let's say you are trying to, this is really where we are moving to construct our first, we'll construct a finite difference method toolkit. So once you have the toolkit, then you can use the toolkit to simulate your physics. Let's start with these partial differential equation of unknown function, which is a function of time and x. So if this is true, you need to discretize your system by using this finite difference method on time. And also you need to run the finite difference method on the space. For this specific case, well, you need to find the derivative with respect to t, derivative with respect to time, x, right? And can you give me an example of a partial differential equation which is a function of time and space? The simplest one is one-dimensional pure advection, right? So you remember this equation. The derivative of the unknown function with t is equal to some constant times u to the x, right? This is a partial differential equation of one-dimensional advection. And anyone knows what is C for the advection equation? This is the velocity field of your system. Right, so you remember this problem. If you know what is C, or velocity of your field, then you can simulate how this point is moving along your domain, right? Okay, so let's see how we can write these discretized form finite difference first order. And I'm just going to use the forward method. Okay, or for this toolkit, I'm just using forward, just for simplicity. Okay, so I'm gonna write the equation. What is the derivative of my unknown function to x? Give me the answer for forward scheme. How are you going to write your unknown function first derivative to x using the forward FDM in a discretized form?
Can I go ahead, Doctor?
Yeah, go ahead.
So as the function is of t and x, it's going to be f of t x like comma x plus delta x.
Well, that is correct, but I'm asking for a discretized form, right?
Mhm.
And discretized form means this form.
Okay, so we can
Right.
just put them in the superscript instead.
Mm-hmm.
Just t and comma and x plus delta x.
Okay, but then in discretized form, we don't have such a thing, right? In discretized form, we have Nijk, right?
Mhm.
This is a discretized form. So we are in forward method, we are trying to use the next value of u, right?
Yeah, true.
In a
True.
space. So this should be I plus 1, right?
Mhm.
Okay, this is with respect to x. So time doesn't matter for the x space discretization. So we are actually standing on the same time. This is n, right?
Mhm.
So because this is in x, then we need to use ui at the same time, right? So it's exactly what we had before, which was in this form, right? However, because your unknown function is a function of time, then you need to add this time superscript as well, right? And same thing happens for discretization in time, right? So let's say if there was no x involved in the system, right? So if the unknown function was only the function of time, then this is how you would write the equation, right? And we did this before, right? But then
Right.
now we're adding one more space here, which you need to write it here, right? So you need to discretize your derivative, right, with respect to space and time, because this is driven by your equation, right?
So, Doctor, in the
Yeah.
discretized form, always the time is in the superscript, right?
Yes, this is the general form, right? So time is always on top, the space on the bottom.
Okay, thank you.
Yeah. And again, these are coming from the Taylor series, right? So if I write these unknown function at a time, and then I'm trying to approximate this unknown function at x naught plus delta x, right? Then you can write this as if I need more space. So this equation is coming from the Taylor series, right? In Taylor series, I'm trying to find this unknown function at a time for this step, or at this point, right? Which is x naught plus delta x. So here I have the first term of a Taylor series, right, which don't have any derivations, then plus delta x divided by 1 factorial times the first derivative of t and x naught. And if I rewrite everything for this first derivative, this is really the discretized form, right? And the same thing happened for a time. So here I'm trying to find the unknown function in a time at t plus delta t, right?
Yeah, right. And after a
At
comma, it's going to be x alone, yeah.
yeah, an x naught, so this is t naught, right? So this is equal to u t naught and x naught, right? Plus delta t ut t and x naught. So this equation is a discretized form of your Taylor series in time. And these two are the key, right? Okay, now when you have these derivatives in a discretized form, right? If you just substitute this in your final equation, then you can rewrite or generate your final discretized equation, okay? So let me make another figure, FDM toolkit. And all these, equations will be a lot more clear, more understandable when you start to write the codes, okay? And you need to review this, of course. But then let's try to write the final equation for 1D advection in a discretized system. My equation is the derivative of u with respect to t is simply just a constant, which is a velocity, a constant velocity times ux. Okay, what I found from the discretized form is that the derivative of u can be approximated by my function at the next grid, same time, minus same time, same grid, divided by delta x. And the discretized form in t, this is going to be, well, now I have to play with time, right? So this is n plus 1 minus u, same time divided by delta t. And as I mentioned, we are forwarding on x because this is a forward method. And also we are forwarding on, or moving forward on time. And because of this, we call this FTFS, forward in time, also forward in space, right? So you could actually have a forward in time, backward in space, or any of the combination of those three different methods that we already talked about, okay? Okay, I have this guy, right? I have this guy. Let's just substitute everything. So the first term is a derivative to ut, which is this one. Okay, u I n plus 1 minus u in divided by delta t. This is equal to minus c. I'm moving to the second term, right? Which is here. So c times okay, now I need to play with the subscript, right? Which is about the space. Using the next space minus the current space grid divided by delta x. Okay, let's see. In terms of the unknown function, I have these four variables. Okay, what is the meaning of this variable? It's the unknown function, right? In next space grid at the same time, at the current time. This is unknown function at the current position, current time. Unknown function, again, current position, current time. Unknown function, current position, next time, right? So can you tell me in this equation, as an engineer or as a simulator, which of these four different variables I need to predict? Which terms are known and which one I'm trying to predict?
Doctor, the ones that I'm trying to predict are the ones that are talking about the next event.
Exactly. So if I have
Yeah.
four variables, what I'm trying to predict is to predict my unknown function for the future, right? And which one is talking about the future?
The one that is derived in terms of time.
Exactly. So this one, this is what I'm really trying to predict. Because it's talking about the future, right? What is happening in the current time, it should be known, right? I'm just trying to find the future event. So now let's try to rewrite everything for these future things, right? So I'm trying to write everything for my unknown function at the next time step, which I'm trying to to predict, and rewrite everything in terms of this one, right? So if I rewrite everything, the final form of the equation is going to be u at the next time step is going to be my unknown function at this point at the current time step minus c times delta t, right? This is going to be here and then divided by delta x times u I plus 1 and minus u I n. This is my final form of the equation. Okay, so this is the velocity field, time steps, x steps, right? And the unknown function for the next grid at this current time, right? And this is a beautiful equation. If you just know your unknown function for the current time and space, right? Then you can guess what is the prediction for the future, right? So let's see how this is going to work in a grid system. I'm gonna grab this equation and borrow this for the next page. Any questions so far? Okay, this is a 1D system, right? So I'm gonna draw the grid in the space. Let's say I have the finite number of grid points. I don't know, 1, 2, 3, 4, 5, 6, right? So in terms of the x, my I is equal to 1, 2, 3, 4, 5, 6. And let's say this is the current time. At time 0, I should have the values, right? Why? Because this is the initial condition. We found that at initial condition, when time is 0, or at current time, we should have all these values, right? This is the initial condition. Okay, next we're gonna move to the next time step, right? So what you see here is the grid in space, and then in this direction, I'm moving for the next time step. Let's say this is t at t naught plus delta t, right? Or this is just one delta t. You need to have, again, the space grid. Nothing has changed. We are actually only moving in a time, right? Okay, now let's say you try to find your unknown function at this point, which is a feature. Okay, now let's look at our final form of the equation, which I just derived. Okay, can you tell me this one, which is right here, right? My unknown function at the grid of I at time step of n plus 1, right? So let's say if this is n, this is n plus 1. Let's look at this equation. Let's see how many of these points we need to find the unknown function at this point, right? So this is equal to my unknown function at the same grid, which is this grid, right? But then the previous stage in terms of time. So I'm using this point, right? So this is this term. Then minus some values, these are given, right? C is the velocity, delta t is given, delta x is given, right? This is delta x. And the difference between the time is really your time step. So you have delta x, yeah, you have delta t. Let's see what we have here. Okay, this is the unknown function at the previous time step because this is n, right? So I'm talking about this time step, but at this grid, right? So this one is the next point in the space, but the previous time step, right? And then you need to again use this point. So by just using these 2 points from the previous time step, right, you can really guess what is going on or what is the prediction of your unknown function at this special point. So once you found this point, then you're going to move to the next point, right? Now you can calculate or predict the value of this point using these 2 points. Then move to the next point, next point, next point, and next point, right? Once you found all these points, then you have the values for the entire next time step, right? Once you have it, then you're going to move one more step in time. And then try to predict your values at the next time step, which is t is equal to t naught plus 2 delta x, right? And again, the same story. For this one, you're going to use the previous, which is now predicted, right? So with this kind of finite difference scheme, right, you can march not only on the space, but also march on the time until you find all the solutions for any given domain of the time and the space, right? So next lecture, we're going to talk about how you're going to use different boundary conditions to solve for these finite difference methods. Just before we end this lecture, in this time space grid, there is actually a special point that you cannot find your prediction. Can you tell me what is that point? Okay, so for this point, it's easy, right? We're gonna use these 2 points. For this point, these 2 points, and we're gonna move on. But what about the very last point?
Yeah, that's what I was thinking of.
So the last point is the problem, okay? Because you need to use 2 points, but then the other guy is not given. And this is about how you should be a little bit more creative on making some imaginary points to help you to find your prediction, and that's about having different type of boundary condition, even either it's a transmissive boundary condition or a solid or a periodic boundary condition. We're going to talk about this, but really the key is just to understand how these schemes working. Just try to have a clear understanding of the grid system, how you march on space, your time, and also please review these equations. I don't ask you to drive anything, right? You need to just understand how these finite difference method is working. So later, we're gonna write some very simple Excel code. And on Monday, probably we should be able to write something on MATLAB too. So be ready for MATLAB. And if you have any question, let me know. The other thing that I can do is probably I can also upload a few other supplemental material, like some simple videos on Brightspace, so that can also help you to have more clear understanding of the concept of finite difference method. Any question? Okay. If not, we're going to see each other on Monday. And because this is an online course, I really encourage you to be more active in the class. So if I ask a question, um, even if you don't know the answer, please try to be more interactive. Unmute your microphone and just say something. Okay. Otherwise, it's going to be a little bit hard for me to just move on. Just try to be don't try, just try to be more interactive with me during the class. Okay. If no question, then we can see each other on Monday. Have a great day. Good night.
Okay, good night.
You too. Thank you.
Thank you.
Thank you. See you.
Thank you, Doctor.
Thank you.
Thank you, Professor.
Sure. Have a great night.